This video is on the logic of hypothesis tests. Let's take this example. A news report claims that boys are more likely to be born than girls. Is this a true statement? How can we find out if it's true or not? Well, we could take a sample. And then we can count how many boys are in the sample and how many girls are in the sample of newborn babies. So we could take a sample and count in the sample and use that sample to estimate the value for the whole population. Not a new idea in statistics class. So let's say we did. Let's say a random sample of 25,468 firstborn children included 13,173 boys. Okay. If you do the division, that means that there's a p-hat of 51.7% boys in that sample. So in that sample, the majority are boys, a small majority, but a majority are boys. Therefore, that must be true that boys are born more often than girls, right? Wrong. That's one sample. There's always sampling variability, right? So it could be that just this one sample by random chance had more boys than girls. Maybe a different sample would have more girls than boys. Maybe another sample would be closer to 50%. Who knows what it is for the population as a whole. But it'd be nice to be able to use our sample to say something about that, right? Because we don't expect every sample to be exactly a 50-50 split. There is always some sampling variability or sampling error. One sample doesn't prove anything. So the big ultimate question is, do these data, this one sample and this one proportion, give convincing evidence that boys are more commonly born than girls? Here's the way we approach it with a hypothesis test. We have the original hypothesis, which is called the Null Hypothesis. The Null Hypothesis is that boys and girls are even. 50% boys are born, 50% girls are born. In the long run, they're even. So we write the Null Hypothesis as H naught, H sub 0. The Null Hypothesis is that boys and girls are the same, so the proportion of boys is 0.5. So P here is the proportion of boys born. Our Null Hypothesis, the hypothesis we begin with, is that they're the same, 50 and 50. The new hypothesis that we get after we take this sample, and the sample seems to suggest something other than 50-50, that's called the alternative hypothesis. We have the Null Hypothesis and the alternative hypothesis. That is that there's more boys than girls. So H sub A, the alternative hypothesis, is that P, the proportion of boys, is actually greater than 0.5. It's not 0.5. It's something bigger, because our sample had a proportion of boys that was bigger than 0.5. A hypothesis test always starts with those two hypotheses, the Null Hypothesis and the alternative hypothesis, where the alternative is suggested by the sample that we've taken. So here's the goal of a hypothesis test, where specifically here we're looking at a hypothesis test for proportions. Our goal is to determine how likely it is for a sample to yield that specific p-hat value, that specific proportion, if the Null Hypothesis is true. So if boys and girls are the same, how likely is it to get, by random chance, a p-hat of 51.7%? Because that could happen by random chance, by sampling variability. So what is the probability then? If we're talking about how likely something is, we're talking about probability. What is the probability of obtaining that p-hat value if the Null Hypothesis is true? So the logic of a hypothesis test is determine that probability. Figure out how likely it is to get a value as big or bigger than what you got if the Null Hypothesis is true. If the probability of doing that, if the probability of getting such a high p-hat value is very small, then it's not likely to have happened by random chance, because it was a very low probability that it would happen by random chance. And we are suspicious enough of the null hypothesis to reject it. We have evidence to reject the null hypothesis and say that null hypothesis was wrong. If that probability is not small enough, then we cannot rule out the possibility of it happening by random chance, because the probability of it happening by random chance is the probability that we just calculated, and it was large enough to say it could happen by random chance. Therefore, we don't have enough evidence from this sample to reject the null hypothesis, and we fail to reject that original null hypothesis. So that's the logic. Figure out that probability, and then decide whether it's too big or small enough to have happened by random chance. So questions you should be asking yourself after I've explained that logic. Number one, how do we determine that probability? Number two, what's considered small enough? And number three, why do we only fail to reject the null hypothesis? Why can't we accept the null hypothesis? So let's dive into those three questions to kind of piece apart, how a hypothesis test works. So question number one, how do we determine that probability? Well, we know that if the sample size is large enough, the sampling distribution of p-hat is approximately normal. The central limit theorem told us that. So we can calculate a probability using the normal distribution. We know how to do that. Normal CDF on our calculator will do that. Normal CDF yields a probability of being below a certain value. When we use the standard normal distribution, normal CDF gives the probability of being below a certain z-score, where the z-score is the standardized score. So what we use is a Z statistic. It's calculated as a z-score with p naught, the proportion from the null hypothesis, the proportion from h naught, as the center of the distribution. So the Z statistic, the test statistic for a hypothesis test for proportions, is p-hat, that is the statistic we got from our sample, minus the null hypothesis, p naught, divided by the standard deviation of p-hat. So p-hat minus p naught over the square root of p-hat, p naught, q naught over n. Note that when we run a hypothesis test, we use the hypothesized proportion, p naught, to calculate the standard deviation. We don't use p-hat like we used for a confidence interval, because our assumption is that p naught is the true value. We run normal CDF with this value, with a mean of 0 and a standard deviation of 1. Whether we want to be above or below the Z statistics, whether we want to go from negative 1,000 up to this Z statistic, or go from the Z statistic up to 10,000, depends on the direction of the alternative hypothesis. In this particular example, we said that we were above 0.5, so we would want to go above. This probability that we obtain via normal CDF is called the p-value. So when we run this hypothesis test, we have these two values we're playing with. The Z, that Z statistic, called the test statistic for a hypothesis test, and then the p-value. Notice it's a capital P, because this is a probability. The probability of getting a value as big or bigger than what we got in our sample, if the null hypothesis were true. Question number two. What is considered small enough? Well, how small of a p-value makes us suspicious that this result could not have occurred simply by random chance due to sampling variability? How small of a probability makes us suspicious? This level is called a significance level, and it's symbolized by the lowercase Greek letter alpha. Unless the problem tells you otherwise, use alpha equal to 0.05. Use a significance level of 0.05, 5%. So we're saying that 5% is the cutoff range. Anything smaller than 5% is so small of a probability that we don't think it happened by random chance. Our conclusion involves comparing the p-value to alpha, comparing the probability we got to alpha. If p is less than alpha, it's not likely to obtain the value we got in our sample by random chance. We have evidence that suggests the null hypothesis is incorrect, and therefore we reject H naught. So if p is low, reject the hoe. If p is low, reject H naught. Reject the hoe. That's a good way to remember it. If p is greater than alpha, it is more likely to obtain this value by random chance, the value we got from our sample. We do not have evidence that suggests the null hypothesis is incorrect. Therefore, we fail to reject H naught. So if p is less than alpha, reject H naught. P is greater than alpha, fail to reject H naught. And that's the language you should use, which might lead to question number 3. Why do we only fail to reject it? Why can't we accept the null hypothesis? Aren't those two the same thing, failing to reject it and accepting it? No, they're not the same thing. All we are showing is that this one sample doesn't give us enough evidence to reject the null hypothesis. Maybe a different sample would provide the evidence to reject it. So maybe it still needs to be rejected, but we just didn't find enough evidence yet. So we should not ever, ever, ever accept the null hypothesis. We can only fail to reject it, because maybe the evidence is out there. So, back to our example. Does our sample provide convincing evidence that boys are more commonly born than girls? Well, let's run the hypothesis test. And the hypothesis test we're running is a 1 proportion Z test. And we're going to run it with alpha equal to 0.05. And we need to state that up front. So we've said that P is the proportion of boys born. Our null hypothesis, H naught, is that P is equal to 0.5. Our alternative hypothesis, which is the hypothesis suggested by the sample we took, is that P is actually greater than 0.5. Because in our sample, our P hat was 0.517. We need to check 3 conditions to make sure that we are actually able to run this test. And we need to write down that and verify that we've checked these conditions. So first, we need a random sample. Well, you can either rewind and check, or believe me that I said it was a random sample of boys. Check. We need to satisfy the 10% condition, because we do have a finite population. There's not an infinite number of people or an infinite number of children born. Well, our sample size was 25,468. We can assume pretty safely that there are more than 254,680 babies born each year. Therefore, we satisfy the 10% condition because our sample size is smaller than 10% of the whole population that we're sampling from. Check. And lastly, we need at least 10 successes and at least 10 failures. So we check NP. We want that to be greater than or equal to 10. Well, NP is 25,468 times 0.5. Notice we're comparing this to the null hypothesis value, not to P hat. Well, that is certainly greater than 10. Half of 25,468 is bigger than 10. And NQ, which is 25,468 times 0.5, is also still greater than 10. So, check. We satisfy all 3 conditions. We can therefore proceed. That's good. Well, the next step then is to find that Z statistic. We have the formula. Z is P hat minus P naught over the square root of P naught Q naught over N. P naught and P are the same thing here. Don't be confused by that notation. So, P hat was 0.517 minus P naught, which is 0.5. That's the null hypothesis value. Divide that by the square root of 0.5 times 0.5, because P naught and Q naught are both 0.5, divided by the square root of the sample size, 25,468. If you work that out in your calculator, you get a Z value of 5.43. So, we then find the probability, capital P, of Z being greater than or equal to 5.43 if the null hypothesis were true. How are we going to find that probability? Normal CDF of 5.43 to, say, 10,000 with a mean of 0 and a standard deviation of 1. We get, and we don't need to write any more work than that, because our work for the hypothesis test is really stating what Z is and stating what the p-value is. We get 2.82 times 10 to the negative 8th. So approximately 0. Very, very, very small probability. That's scientific notation with 7 zeros and then a 2. Okay, so we take our 0, our p-value, which is almost 0, and we compare it to the alpha that we identified up front. We said we're going to take a significance level of 0.05. We compare our p-value to that. Well, 2.82 times 10 to the negative 8th, or approximately 0, is certainly less than 0.05. But we need to write that, show that we've compared the two. So that means we can make our conclusion. Since p, which is approximately 0, is less than 0.05, we reject H naught. We have convincing evidence that the true proportion of boys born is greater than 0.5. That's exactly the way we should write our conclusion. First, comparing p to alpha, then the immediate implication of either rejecting H naught or failing to reject H naught. Since p was less than alpha, we reject H naught here. And we have convincing evidence that the true proportion of boys is greater than 0.5. The end.